Hello everyone. So we are discussing resistivity. So we talk about resistors. We use resistors in circuits, and what determines the resistance of a particular resistor. So for an example, if we have, let's say, a small resistor, resistors typically they're cylindrical devices. There's color bands that helps us to figure out what the resistance is. Let's say, for an example, this is a 200 ohm resistor. So what are the factors that determine resistance? It depends on a couple of things. If you go back to the slide on the side, resistance of a wire. Now, it doesn't need to be an actual resistor component, like an electrical component such as a resistor. It can be a conducting wire, right? In a circuit, you have resistors, you have light bulbs and all that, and then you have these connecting wires. They also have some resistance. Inside the resistor also it is a conductor with certain resistance, right? If you think about a light bulb, there is also a conducting wire inside, which has a lot of resistance. That's why it heats up and emits light. So resistor is, at the end, it's a conductor and depends on the properties the resistance is determined. So resistance of a wire is directly proportional to its length, inversely proportional to the cross-sectional area. Means if you compare two wires, the same material, let's say here one wire with some length L, here's another one a little shorter. Resistance is proportional to length. If everything else is same, if it is the same material and if they both have the same cross-sectional area, this is L, this is little bit of L, right? This is bigger. Resistance is proportional to the length, means longer the wire, more resistance it has. Inversely proportional to the cross-sectional area. Let's say we take the same wire, same material, take the same length, this is L, this is area, and then we much wider, thicker one, same length, bigger area. Resistance is proportional inversely to the area. That means bigger the area, less resistance, less ohms it has. For an example, let's say this is 100 ohms. If this is double the length, this will be 200 ohms. If this is, let's say, 10 ohms, this is cross-section half of that. So the resistance increase, resistance get doubled. So this will be 20 ohms. So like that. With the length, resistance increase. With the cross-section, resistance decrease. Also depends on what kind of material. Those chemical properties, these materialistic properties, are given by something called the resistivity. It's a characteristics to the material. Depends on what kind of chemical bonds it has, the separation between atoms inside, all those chemical stuff. So it's a material property. We name it as resistivity of the material, denoted by the symbol this. It's rho, resistivity, So resistance depends on three things: length, area, and resistivity. And when you put them in an equation, we get this equation: resistance equals rho L over A. So bigger the rho number, bigger the resistivity, more resistance. Bigger the length, more resistance. Bigger the area, less resistance. When we say area, we talk about this cross-sectional area, right? Not the cylindrical side, but the cross-section. Okay, so looking at this, what about the units of resistivity? We can plug units to everything else. Here, this is ohms, this is meters squared, this is this is meters squared. So if I take rho to the other side, and then plug these units, ohms times meters squared over meters, cancels out, ohm meter. Units of resistivity is ohm meters. So once again, resistance depends on these factors, length, area, and resistivity, and given by this equation over here. On the PowerPoint you can see the equation. Equation is right here. Let's get into some example problems. Okay, so let me clear the page. Alright, so what kind of examples? Let's say we have a piece of copper, a wire made out of copper. It's 2 meters long, that's length is 2 meters, and the cross section is let's say 3 millimeters square of cross section. Let's say 0.3 millimeter. So there's a piece of wire made out of copper, has a length of 2 meters and a cross-sectional area of 0.3 millimeters. So it's a cylindrical shape linear object. Now the question is, what is the resistance of this wire? If I want to convert this into a resistor, if I want to use this as a resistor, what's the resistance? Now we're going to use the equation resistance equals rho L over A. I have the length, I have the cross-sectional area. What about the resistivity, that material property, resistivity of copper? Where do I find that? So for that, we're going to go to these resistivity tables. So let's go to the next slide. Here you can see the table is a little small here. Let's look at the first and the second columns for the time being. Let's not worry about the third one for now. So here's different materials, conductors, silver, copper, gold, and all that. Here's the resistivities, the numbers given here in this second column. Also important to note is that it says this table gives the resistivity at 20 Celsius and temperature coefficient. So we are looking at these numbers, but these resistivities are defined for 20 Celsius. So resistivity changes with temperature. Earlier we said resistance change with temperature, right? We talked about this last time. Resistance goes up when temperature goes up for most of the material. It's directly proportional. Why it's happening? A major reason is this resistivity. Resistivity is sensitive to temperature. When temperature changes, resistivity changes. Length and cross-section also changes. Things expand, right? Conductors, metals, they expand when you increase the temperature. But compared to the resistivity changes, most of the time we can assume those expansions are not that significant. If you have a very long, thin conductor like railway tracks, probably many meters long. If you think about it like a single piece of track, many meters long, like 50 meters long, maybe not 50, 20 meters long. When temperature changes by a couple of degrees, the length changes by probably like few centimeters maybe. But resistivity has very significant measurable changes. Okay, so how do we do this? And why temperature is important? Whenever we do these kind of calculations, we have to mention at what temperature. So in these questions, usually we say find the resistance at 20 Celsius. We consider 20 Celsius as the room temperature. Okay, standard room temperature. There are different standards. Sometimes some people take 0 Celsius as the standard temperature. Some take 25 as the standard. Most of the time we stick with 20, and all these numbers are defined for 20. So let's say here's a piece of conductor, a copper wire given. This is the length, this is the cross section. At 20 Celsius, what is the resistance? So that's how the question is going to be worded. Okay, alright, so let's find this. So resistance equals this number. Resistivity for copper, it's 1.68 times 10 to the negative 8 multiplied by length 2 divided by cross-section area 0.3 millimeters squared. So millimeters to meters divided by 1000. Millimeters squared divided by 1000 twice. So multiply by 10 to the negative 6. Instead of negative 3, we have to multiply it by negative 6. So what do we get? Take the calculator. 6, negative 2. Take the calculator, plug in the numbers. I have 11.2 times 10 to the negative 2 ohms, or 1.12 times 10 to the negative 1 ohm, or 0.112. Yep, that's right, 112 ohms. So it's a small resistance, and it makes sense because this is copper. Very small resistance anyways, resistivity is very low. So this is how we calculate the resistance. Alright, so the equation we need to know is this. Now you see, if you go back to the table, when you go down the table, the resistivities increase. Like silver, copper, gold, they're good conductors, so small resistance. And as you go down, you see that mercury has significantly high resistance, nichrome or nichrome. Compared to copper, it's probably like 70 times bigger, right? So nichrome is one of the materials we use in light bulbs. This thing, it's actually the physical structure looks like this: the glass area, the metal connection, and here there's a metal coil. This is made out of nichrome. When current goes through it, because of the high resistivity, it heats up, and that's what we get as light. When you go down the list, we are switching to semiconductors, much higher resistivities, and then we go to insulators, glass and hard rubber. You see very, very high resistivity. So that's why these things are called insulators. The resistance or resistivity is really high. Okay, so we did one example. Let's see what else we have. Alright, let's try this problem. So you guys read it, you try it first, and then get to the video. Suppose you want to connect your stereo to remote speakers. If each wire must be 20 meters long, what diameter copper wire should you use to keep the resistance less than 0.1 ohm per wire? So you are connecting your music player to the speakers which are 20 meters away. Now the connecting wires, if there's a lot of resistance in them, they're going to take up a lot of voltage. So the speakers will be receiving less voltage, there will be less sound. The more voltage you have, more sound you get, more current, more voltage you, less resistance in the wire means more current through the wire, so the more loudness, more intensity. So we need to keep the resistance low, we need to keep it at 0.1 ohms. So what do? Okay, so resistance should be 0.1 ohms maximum. Length of the wires is 20 meters long. What diameter copper wire? Again we are using copper wires, so resistivity is 1.68 times 10 to the negative 8. Now here we're going to assume that things are happening at room temperature, so 20 Celsius, so we can use this number. What is the diameter should be? So diameter, now these are circular wires, right? So the face or the cross section is going to be circle. This is the diameter. So let's find the area and then we can get to the diameter later. Alright, so what's the area? So resistance is rho L over A. A is rho L over R. 1.68 times 10 to the negative 8. 20 meters divided by resistance 0.1. Looks like math is not that bad. 1 times 10 to the negative 1, so cancels out, negative 7, cancels out, negative 6, negative 6, that's the area, so this is meter squared. So what's the diameter? We know that area for a circle is pi r squared. So let's find the radius. So we have r equals area over pi square root. So let's take the calculator and do the math. I have 1.03 times 10 to the negative 3 meters. That means 1.03 millimeters. That's the radius. So diameter will be twice that, 2.46 millimeters. So I need wires with 2 millimeter diameter in order to effectively transport current from the system to the speakers. Okay. Question number 2 asks, saying that if the current to each speaker is 4 amps, what is the potential difference or voltage drop across each wire? So let me erase something here, make some space. Okay, so here's the music controlling unit, whatever it is. Here's the speakers, and here's the connecting wire. This is 20 meters long. We found the resistance to be 0.1 ohms. Now this is like it is actually like a resistor in it, right? That's the idea. Resistance is 0.1 ohms. We are drawing a current of 4 amps. So this whole thing, from here to here, there will be some voltage because of this resistance. You don't have to draw a resistor here. You know what the resistance is. I'm just trying to show that this thing acts like a resistor. So what voltage does it create? V equals IR, current, times 0.1, so 0.4 volts. So the voltage from here to here is 0.4. What does that mean? Let's say let's say what am I trying to say here? Hold on. Okay, so let's say, for an example, the music system, the control unit, is creating a voltage of 10 volts. Ideally, you want the speakers to receive 10 volts, but there is a drop on the way, 0.4 volts. So the actual voltage it receives is 10 minus 0.4, which is 9.6 volts. So that's the idea of voltage drop, right? In the way from one place to the other, if there are resistance on the path, it's going to drain some voltage from the supply, and in this case it's taking 0.4 volts out. So that's the drop through the wires, and then the setup receives, speaker receives 9.6 volts. Okay. All right, let's move on. Okay, so let's see what else we have. So we will work on few more example problems in class. Conceptual example: stretching a wire changes resistance. Suppose a wire of resistance R could be stretched uniformly until it was twice its original length. What would happen to its resistance? Okay, so think about it. You have a wire like this. Has some length, some area, and then you're going to stretch it till the length is doubled. Now it's 2L. What happens to the resistance R? That's the question. Now what's going on here? We know that resistance is given by rho L over A. Now, just because you stretch or compress the wire, this is not going to change, right? This can change with the temperature, but physically stretching it won't change resistivity much in a measurable way. But when you stretch it, the length get doubled. Now instead of L, it's 2L. What do you think about the cross section? Is that going to stay the same? Is it still going to be this big and longer? That's not possible, right? The volume remains the same regardless you stretch it or compress it. Volume remains the same, means when you increase the length in the same ratio, the cross section needs to decrease. So A will be half now. So when you increase the length, when you double the length, resistance get doubled. When you decrease this by half, resistance get doubled. As a result, resistance will be increased by 4 times. The new resistance, if this was 100 ohms, now we have 400 ohms. Okay. Alright, let's move on. Okay, so the next topic is we're going to study how resistivity or resistance changes with temperature. So let me clear this. Right. Now you guys know that resistance and temperature are related. Why? Because resistivity and temperature are related. For most of the conductors, when temperature goes up, resistance goes up, and vice versa. They are directly proportional. Okay? There are some specific alloys, special materials, special compounds works the other way. Resistance goes up, temperature goes up, resistivity goes down. That's very unique. You might see some examples of those. So, using this property, very sensitive thermometers are built, and there are so many other applications as well. One good example that we use in science labs is these electrical thermometers that use the resistivity. Okay, so let's see what the equation looks like. Let's go to the next slide. Resistivity. Resistivity increases with temperature and is given by this equation. What is this equation? Rho T equals rho naught 1 plus alpha T minus T naught, close brackets. Looks like a little complicated equation, but let's see what each term means. This is the resistivity at the given temperature, at temperature T. Like if you want to find the resistivity at 50 Celsius, that this T will be 50, right? At given or interested or required temperature at given temp. This is resistivity at the standard room temperature, or in other words at 20 Celsius. 1 plus alpha, this is the temperature coefficient of resistivity. This tells you how much it changes per 1 degree. Remember, we measure things in either Celsius or Kelvin. Here there's a difference, so it doesn't matter whether we use Celsius or Kelvin, but we can't use Fahrenheit. Alright. So this is the temperature we are interested. Like we want the resistivity at, let's say, 50 Celsius, 50 goes here. So this is the given temp. This is the standard temperature, or the room temperature, which is 20 Celsius. Okay. So, how do you use this equation? So, for an example, let's say somebody says, find resistivity of aluminum at 100 Celsius. How do you do that? Use the equation rho T equals rho naught 1 plus alpha for aluminum T minus T naught. Resistivity at 100 Celsius, rho 100 Celsius, rho 20, 1 plus alpha aluminum 100, that's the temperature, minus 20. Now, alpha aluminum, we go back to the table, right? Let me show you the table. Look for this column, third column, temperature coefficient. Per Celsius, where's aluminum? 0.00429 per Celsius. So that's what goes here. So let me write this again. Rho 100 equals rho 20. Resistivity at 20 degrees for aluminum, it's right here, 2.65. 10 to the negative 8, 1 plus alpha aluminum, 00429, open bracket, 100 minus 20, actually 100 minus 20 is what? 80, right? 80 is here. Now take the calculator and do the math. Okay, so we do expect a higher resistivity, right? We are looking at resistivity at a higher temperature, at 100 Celsius, so it has to be higher than what it was. So when you do the math, you actually get a higher number, 3.55 10 to the 8 negative ohm meter. So this is how we find resistivity. This is how we use the resistivity and temperature equation. Okay, let's try another one. Okay, let's try this. Oh, before that, I need to mention something to you guys. Now, let me take a new page. Alright, I gave you the equation rho t, rho no, 1 plus alpha t minus t naught. So this is a resistivity equation. Now, by assuming that dimensions, length and cross section doesn't change much with the temperature, they do change a little bit, but by assuming they remain the same, negligible changes, we can transform this into a resistance equation. We know that resistance is rho L over A. So therefore, rho is RA over L. So I can rewrite this. Instead of rho T, I can say RT A over L equals R naught A over L and the rest of it. If we assume the cross section and length doesn't change, we can cancel this on either side of the equation. So I can write the equation, the above one, for the resistance, which is more useful than resistivity. Resistance at any temperature, resistance at 20 Celsius or the standard given temperature, 1 plus alpha t minus t naught. This is also equally or even more useful. So resistance at any temperature is, at a given temperature, is resistance at standard temperature and then within bracket all that. Let's look at this problem. Resistance thermometer. The variation in electrical resistance with temperature can be used to make precise temperature measurements. Platinum is commonly used since it is relatively free from corrosive effects and has a high melting point. Suppose at 20 Celsius the resistance of platinum meter is this. So you guys, why don't you go ahead and do the math first, and then I keep saying this from now on, that's what you should do, okay? Do it first and then look for the answer. (20°C), the resistance is 164, so that's R naught. 164.2 ohms. This is at 20 Celsius. That's why we take it as R naught. When placed in a particular solution, the resistance is 187.4. So that is actually your RT. At a particular temperature, we can read the new resistance, which is RT. We don't know what the temperature is, but we have the resistance. It looks like it is higher than 20 Celsius. That's why it has a higher resistance number. This is the T temperature which we are trying to find out. What is the temperature of this solution? So asking what is this T temperature. Okay, use the equation. RT 187.4 equals R0 164.2. 1 plus alpha. Now this is, what is it? Platinum. So go to the table. Look for platinum. 10.6 times 10 to the negative 8. 10.6 times 10 to the negative 8. Open bracket. T minus. We don't know the temperature now. So we take it as T minus this one, 20. Close the bracket. Now this is what we need to do and solve for T, and that gives you what the temperature is of this solution. So I'm going to pause it and then we'll come back with the answer. Okay, looks like I have made a mistake here, right here. It's the temperature coefficient. I put the resistivity, so let me go back and check what it is. Let's go to the table. There you go. Platinum, this is what I put. What I should have used is this 0.0039. So let me change that. 003927. Okay, so do the math. Divide to the other side. 164.2 equals 1 plus this whole thing, 3927, T minus 20. Subtract 1 from this. So do all that. I get approximately 55.9. So T equals 55.9, or approximately 56 Celsius. Okay, so using temperature coefficient in an example. Alright, what else? So next topic is electric power. We'll get to that later, but for now this is what we need to focus on. Resistivity, how to find the resistivity when the dimensions given, when the length, cross section and all that given, how to find the resistance using resistivity, and then temperature stuff, like for an example, what's the resistivity at a particular temperature, or what's the resistance at a particular temperature, those kind of things. Or if the temperature is given, what the resistance would be, right? Okay, so that's all for this segment. Thank you, everyone.